In this example problem, we're going to look at 1 kilogram of steam condensing in a cold room, or I guess in a 25°C room at constant pressure. We know that this process happens spontaneously. If you have steam at 100°C and you put it in a room at 25°C, that steam will condense and turn into liquid water. This happens spontaneously. So what we know about entropy, this should be a positive. Delta S of the universe should go up because this is a process that actually does occur. It does happen. So let's do some calculations and figure out if that's true. We're going to start with this equation, our entropy balance, if you will. Delta S equal Q in over T in minus Q out over T out plus S gen. So where we're going to start is looking at the entropy change of the water. So this is delta S of the water itself as it's condensing. So that water is losing heat. That means its entropy is actually going to be going down. This is equal to the mass times delta lowercase s. So I'll make that a little bit more clear that that's a capital letter, which is equal to the mass. So it's turning from a gas into a liquid. So this would be SF minus SG, which is just equal to the mass times negative SFG. So if we look up in our steam tables what the value is for SFG, we can find that delta S, capital S of our water, is equal to, we have 1 kilogram of water, so 1 kilogram times negative 6.0480 kilojoules per kilogram Kelvin, or minus 6.048 kilojoules per Kelvin, because we have 1 kilogram. So that's how much the water is changing entropy. Hopefully other things are changing entropy more than that so that we actually make up for it. So let's look at what that is. And now we have to look at what's happening with heat. So that's where entropy changes. It changes when heat is moving from one place to another. So where is heat moving? Well, we have heat moving from the steam into the room. It's a constant pressure process. So we have constant pressure. So our energy balance is delta U equals Q minus W. W equals the integral of P dV, which is equal to just P delta V for this particular case. Then we can write Q equals delta U plus P delta V. And this, again, maybe you don't recognize it, but this is just equal to delta H. Right? H being equal to U plus quantity PV. So that's just delta H in disguise. Okay, so how much heat we have transferring from the water into the room is equal to the change in enthalpy, H, of the water. So let's calculate what that is. So delta H of the water is equal to the mass, again, times H F minus H. So it's, H F minus Hg. So that equals 1 kilogram times minus HFg. So that equals negative 2257 kilojoules. Out of the water. Okay, so this is where things get a little bit confusing, but hopefully not too bad. So it's going, Q is going out of the water. That's what our negative sign means. So this is, right, that's what the negative sign means. So we'll put the magnitude of that as Q out. Okay, so let's start plugging things in. So we have delta S equals Q in over T in minus Q out over T out plus S gen. There's our equation. So delta S is negative 6.048 kilojoules per Kelvin. That's how much the entropy of the water is changing. Q in is equal to 0. So there is no heat coming from some other source, some hotter source than the water, where heat is coming into the water. So this term, that first term cancels out. We calculated here 2257 kilojoules out. So we have 2257 kilojoules coming out of the water and going into the room. So that's the temperature that it's going in, that it's going at. So this is T out equals T room, which is 25 degrees C. But when we're doing things with entropy, we have to use, 20 degrees C, I believe. Is that right? 25 degrees C. When we're doing things with entropy, we have to use Kelvin. So that equals 298 Kelvin. Then if we want to calculate S gen is equal to 2257 kilojoules divided by 298.15 Kelvin plus negative 6.048 kilojoules per Kelvin. It just so happens this first term is 7.57 kilojoules per Kelvin minus, so that's how much the entropy of the room is changing. If you want to think about it that way, the room is increasing in entropy by 7.57 kilojoules per Kelvin. The water is decreasing in entropy by 6.048 kilojoules per Kelvin. So the net effect is that S gen is a positive number, and it is 1.522 kilojoules per Kelvin. Again, Sgen being positive is a good thing because we know that this is a spontaneous process that would happen automatically. Figuring out how to do the sign convention for these problems is going to be a little bit challenging to figure out where our negatives should be, where our positives should be. You saw up here, I actually kind of flipped the sign a little bit when I put it here, because this sign, when I calculated it over here, that told me it was going out of the water. The heat was leaving the water. Maybe could have just figured it out by thinking about the problem. I know the water's cooling down, must be heat going out of the water. So you're putting into here, or into here, not the sign, but you're putting in the magnitude of the heat that's coming into the system or the magnitude of the heat that's going out of the system. And then the temperatures that you're using. So the temperature out, that's not the temperature of the water, that's the temperature where the heat is going to. So again, that's the temperature of the room. So hopefully this makes sense. We'll have one more practice problem and then a couple other times for you to kind of get some practice by yourself before you embark on the homework. So make sure to watch the second video where we talk a little bit about how to do some of the same types of things, but then with the added complication of rate.